Hi everyone, in this video we are going to discuss this example. So this real integral we have and we have to find its value with the help of residue. Actually the residue concept is related with complex valued function, but we are going to use it to find the value of this integration. Okay, so let us call the given integral as I. We have I is equal to integration minus infinity to infinity x square upon x raised to 6 plus 1 dx. Okay, so we can easily find the value of this real integral with the help of residue. But see, there is fixed method. We are going to follow it to solve this problem. So let us recall the method first. We will discuss the method first and then we will talk about this problem. Okay, so we should have integral of this type minus infinity to infinity p of x upon q of x dx. So when you have this type of integral, then we can apply this method. Okay, so limit should be always minus infinity to infinity p of x and q of x. These are polynomials in x. Here also in example we have at numerator we have one polynomial and in denominator we have another polynomial. So the condition is degree of q of x is greater than or equal to degree of p of x plus 2. Okay, so degree of q of x must be greater than or equal to degree of p of x at least by 2. Here also you can easily see degree of here numerator is 2 and degree of denominator is 6. So definitely we can apply this method. After that what we do one construction. Okay, so actually some theory part is there behind this example, behind this method. We are not going to discuss the theory in details. I am giving the importance to the solution of this problem right now. Okay, so I will tell you the theory in brief. So here we consider a semicircle, okay, in which is in upper half of a plane and the diameter along the real axis minus r to r. Then we tend r tends to infinity. R tends to infinity, that means it will go to minus infinity. On that side it will go to infinity. So here we get a large semicircle. That means it will expand like this and it will cover the entire upper half of a plane. So this is the logic behind it. After that we consider the function f of z. Whatever the function we have, we replace x by z and then we get f of z. We find the singular points of f of z. Singular points means what? Means a point where the function is not analytic. Okay, not analytic, or generally we say the point where the denominator is 0. And we find their position. Some singular points can be here, somewhere here. Getting? So we give importance to the singular points which lie in the upper half of a plane like this. These singular points lie in the upper half of a plane. We find the residues at those points and the value of integration is 2 pi I sum of residues. So in this way we find a value of, we find a value of real integral with the concept of residue. So the same method we are going to follow here. Okay, I have already written the integral. So here f of z, let me write f of z, that means if you replace x by z, you get a f of z, z square upon z raised to 6 plus 1. Okay, so now I will write the entire thing what I told you here, that I consider a large semicircle. Okay, so let me clearly mention here, we consider a counter with a large semicircle centered at origin and lies in upper half. Okay, it lies in upper half of a plane and diameter along a real axis, right? So I have written the same thing here. So let me remove this part, so we will have some more space to write. So as we have already discussed, the given function satisfies the condition of this method. Okay, the condition is degree of denominator 6. It should be greater than degree of numerator at least by 2. That means here degree of denominator greater than or equal to degree of numerator plus 2. Getting? Or same thing we can write in this way, z f of z tends to 0, z f of z tends to 0 as z tends to infinity, mod z tends to infinity, mod z tends to infinity. Okay, so see, both statements having the same meaning. If you understood this one, you can write this one only. Okay, after that I will find the singular points of this function. Singular points, that means a point where the function is not analytic, or simply we say the point where the denominator is 0. So actually in denominator we have a polynomial of degree 6. It will have 6 roots. We supposed to find the factors, but see, it's very complicated and it is not easy to find the factors. So that's why I will simply mention f is not analytic, f is not analytic if the denominator, that means z raised to 6 plus 1 is equal to 0. Okay, when the z raised to 6 plus 1 will be 0, that means denominator will be 0 and function won't be analytic and we get a singular point, right? See, z raised to 6 plus 1 is equal to 0. This is equation of degree 6. It will have 6 roots. We have to find all those 6 roots. So let us solve it. Therefore, z raised to 6 is equal to minus 1. I shifted minus 1 on that side. We got minus 1. Minus 1 means minus 1 plus 0i. Getting? So basically it's a complex number. So that's why I wrote real part plus imaginary part. Imaginary part was not there. So that means it is 0. Minus 1 plus 0i. So I'm sure you are familiar with this fact that z is equal to x plus iy. This is a complex number and it is in its Cartesian form. Z is equal to r e raised to I theta. This is exponential form, and z is equal to r cos theta plus I sin theta. That is polar form. That means if you have any complex number, it can be expressed in these 3 different ways. So here we have a Cartesian form. You can easily see x minus 1 y 0, but if we express this complex number in a polar form, easily we can find all its roots. Okay, so let us try to express in this polar form. Minus 1, that means we can write cos pi plus I. 0, that means sin pi, right? Cos pi is minus 1, sin pi is 0. So that means I express in this form cos theta plus I sin theta. R is not there, that means R is 1. Okay. After that, what will I do? I will take 6th root of both sides. So cos pi plus I sin pi whole raised to 1 by 6. I took 6th root of both sides. Okay. So after solving it, it is expected to get roots, but see, the power is 6. That means it is expected to get 6 different roots. Let us try to find. Okay. So let me remove this part, so we will have some more space to write. Okay. See, after that, what will I do? I will write z is equal to cos 2n pi plus I sin 2n pi plus pi raised to 1 by 6. 2n pi, 2 pi, that means 360 degree, that means 1 complete circle. So if you have any complex number here and if you complete a circle, it reaches at the same position. It means if you add 2n pi, that means n number of circles, okay, so then you will get the same position of a given complex number. It means it doesn't matter. Now the question is, why I am adding this 2n pi? Because we want 6 different roots. So that's why I am adding 2n pi, so we can easily get 6 roots. Now I am applying de Moivre's theorem. It says that 1 by 6 will come here. It will be the multiple of that angle by de Moivre's theorem. 2n pi plus pi divided by 6. 6 will come here, I sin. On this side also 2n pi plus pi divided by 6. and here n varies from 0, 1, 2, 3, 4, 5. Okay, 0, 1, 2, 3, 4, 5. That means yes, if you take n is equal to 6, then again you will get the same value which we get for 0. Now I will put n is equal to 0, 1, 2, 3, 4, 5. Okay, then we will get 6 different roots. Then roots are, I am going to write the roots. Let us call it as alpha naught. I am going to put n is equal to 0 here. So cos 0, that means we will get cos pi by 6 plus I sin pi by 6. So it can be expressed as e raised to I pi by 6. Since you know that e raised to I theta is cos theta plus I sin theta. If you don't know, let me tell you that e raised to I theta is equal to cos theta plus I sin theta. So this is the relation we have and I am using it. Why I am expressing in an exponential form? Since it will be more simple. If you keep in this way, cos and sin doesn't matter, final answer will be same. But if I express in exponential form, it will be very easy to handle. Now I will put n is equal to 1, then we will have alpha 1 and I am putting 1. So 2 pi plus pi 3 pi cos 3 pi by 6 plus I sin 3 pi by 6 e raised to I 3 pi by 6. 3 cancel, e raised to pi I by 2. After cancelling 3, I will get e raised to pi I by 2. So this is our second root. In the same way, we will find the remaining 4 roots. Just make a screenshot of it, then we will go further. So now let us put n is equal to 2. Therefore, alpha 2 cos, I am putting n is equal to 2. 2 into 2, 4 plus 1. 5 pi by 6 plus I sin 5 pi by 6 in exponential form e raised to 5 pi I by 6. Alpha 3, I am putting n is equal to 3 here. Cos 3, no, 3 into 2, 6 plus 1, 7. 7 pi by 6 plus I sin 7 pi by 6, that means e raised to 7 pi I by 6. Alpha 4, right, I am putting n is equal to 4. 4 into 2, 8 plus 1, 9. Cos 9 pi by 6 plus I sin 9 pi by 6 e raised to is equal to e raised to, see 3 will get cancelled, no. So e raised to 3 pi I by 2. 9 pi by 6 actually, but 3 get cancelled. So 3 by 2. So I wrote in this way. N is equal to 5, last root, cos 5 into 2, 10 plus 1, 11, cos 11 pi by 6 plus I sin 11 pi by 6. It means e raised to 11 pi I by 6. So we got 6 different roots. Okay, so now we have to find out which roots are lying in the upper half of a plane, right? See, by observing the angle we can easily guess. So this is a complex plane, getting. So for alpha 0 we have angle pi by 6, that means 30 degree. 30 degree, that means somewhere here, getting, you can easily see 30 degree. So the first alpha naught lies somewhere here. Alpha 1 pi by 2, 90 degree, it will be here. Alpha 2 5 pi by 6, 5 pi by 6 means 150 degree, it will be somewhere here, getting. Alpha 3 7 pi by 6, 210 degree, that means it will be here, getting. 3 pi by 2, that means 270 degree, it will be here. And 11 pi by 6, that means it will be somewhere here, getting. So see, total, this is alpha naught, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. So there are total 6 roots. Out of them, alpha naught, alpha 1 and alpha 2 lie in the upper half of a plane, and remaining 3 roots lie in the lower half of a plane. So we are more interested in these 3 roots. Okay, so let me clearly mention, but only alpha naught, alpha 1 and alpha 2 lie in upper upper half of a plane. It means we will find residues only at alpha naught, alpha 1 and alpha 2. Okay, just make a screenshot of it, then I will go further. So let us find residues at alpha naught first. Okay, so residue of f of z at z is equal to alpha naught, right? See, actually we have six different roots, and fortunately all these are simple poles. So when we have simple poles, we have very simple formula to calculate residue, and I am going to use the same. That formula is limit z tends to alpha naught z minus alpha naught f of z. Okay, so this is equal to limit z tends to alpha naught z minus alpha naught. What is my f of z? My f of z was z square upon z raised to 6 plus 1. This is my f of z, right? So the problem is that if I put z is equal to alpha naught here, if I apply the limit, if I put z is equal to alpha naught minus alpha naught 0. If I put alpha naught here, but see, alpha naught is a root of this z raised to 6 plus 1, that means obviously it will give 0. It means we are getting 0 upon 0 form. Do you know what we do if I get 0 upon 0 form? We have to apply L'Hospital's rule. Here also I will do the same. Okay, 0 upon 0 form. So L'Hospital's rule. So that rule says we have to take the derivative of numerator divided by derivative of denominator. Okay, z raised to 6 plus 1. So I should mention by L'Hospital's rule. Okay, I will write in short by L'Hospital's rule. That's it. So let us take derivative. So this is equal to limit z tends to alpha naught. See, u into v formula we have to use. First into z minus alpha naught, its derivative 2z plus z square as it is. Derivative of z is 1, alpha naught is 0, so we get 1 only. Getting? So I use u into v formula, first into derivative of second plus second into derivative of first. Let us talk about denominator. Its derivative will be 6z raised to 5. So let us apply the limit. If I put z is equal to alpha naught minus alpha naught 0, 0 into anything 0 plus here alpha naught square. In denominator 6 alpha naught raised to 5. See that alpha naught square will get cancelled and we will get 1 upon 6 alpha naught raised to cube. Getting? So at alpha naught we found out the residue and we got this one. Similarly, we have to find residue at alpha 1 and alpha 2. So without doing actual calculation, we can easily guess for alpha 1 the residue will be 1 upon 6 alpha 1 raised to 3, and for alpha 2 we will get residue 1 upon 6 alpha 2 raised to 3. Okay. So let me clearly write here. So I have clearly mentioned the residues here. Okay. Residue at alpha 1 will be 1 upon 6 alpha 1 cube. Residue at alpha 2 will be 1 upon 6 alpha 2 raised to 3. So out of 6 that singular points, only 3 were lying in the upper half of a plane and we calculated residues for them. So let us go for the last step. Then that integration minus infinity to infinity x square upon x raised to 6 plus 1 dx is equal to 2 pi I sum of residues, right? So this is equal to 2 pi I. The first residue 1 upon 6 alpha naught raised to 3. Second 1 upon 6 alpha 1 raised to 3. 1 upon 6 alpha 2 raised to 3. So 6 we can take common. 2 pi I upon 6. 1 upon alpha naught raised to 3. 1 upon alpha 1 raised to 3. 1 upon alpha 2 raised to 3. Okay, just make a screenshot of it, then we will go further. So let us do that calculation. Getting? 2 will get cancelled here. Pi I by 3 alpha naught, it was e raised to I pi by 6. So this was the value of alpha naught plus alpha 1, its value was e raised to I pi by 2 power is 3, and the last one is e raised to 5 pi I by 6 raised to 3. So we are putting the values of alpha naught, alpha 1 and alpha 2. Let us simplify it further. Pi I by 3. So if you take product, e raised to I pi by 2 plus 1 upon e raised to 3 pi I by 2, 1 upon 3 will get cancelled, e raised to 5 pi I by 2. Now what I am doing, I am going to shift all these terms to the numerator. So power will, sign of that power will get changed. E raised to minus I pi by 2 minus 3 pi I by 2 minus 5 pi I by 2. Okay, so I am going to express in terms of cos and sine. E raised to I theta is cos theta plus I sin theta. Okay, and if you have a minus sign, here also we should write minus sign. So I am going to write there pi I by 3 cos pi by 2 minus I sin pi by 2. For this one, cos 3 pi by 2 minus I sin pi by 2. For last one, cos 5 pi by 2 minus I sin 5 pi by 2. Okay, so now we want the values of all these terms. Getting? Using calculator, you can easily find the values of cos pi by 2, cos 3 pi by 2 and so on. Getting? So just let me write directly. Cos pi by 2 0, sin pi by 2 1. Getting? So it will be minus sign. Cos 3 pi by 2 0, and sin, here I should write 3 pi by 2, that will be minus 1, minus minus plus I. Cos 5 by 2 0, and sin 5 pi by 2 will be, see, it will be 1, so it will be minus I. So plus I minus I will get cancelled, pi I by 3 and this minus I. So minus pi I square by 3, I square is minus 1 upon 3, minus minus plus pi by 3, this is required answer. Okay, so just make a screenshot of it, then we will stop. Thank you. See you in next video.